want to thank, first of all, AMITI for hosting us and be the first investor in NextSilicon. Here you are. Yeah, and obviously Samsung. And when Ben and Ruti asked me to talk, I thought about, okay, innovating in next generation compute makes sense. And as Ruti mentioned, this is my collection. And yes, I'm a software engineer. This is what I did when I was young. I enjoy writing code in x86 assembler, and we have a few Commodores kind of machine. And I want to thank all of you for missing the World Cup. Now it's Mexico versus Saudi. I don't know what's the bets are because I bet on that. We'll see. So I'm a software engineer. This is what I did, being an A200, and before, and after that I founded a service company that Mellanox acquired, and then I came to the hardware world. I never done it, but I enjoyed doing the low-level portion. And the reason why in the offices there is the collection of the old computer is next generation. You need to learn from the past what is different in order to be successful. How many companies here are doing custom silicon? Just yeah. Why? Don't do that. Okay. So this is me, and yeah. Today I'm not going to tell you anything about NextSilicon. Okay. We are still in stealth. This is Elizabeth, and Elizabeth was the developer of ARPANET, prior to the Ethernet that everyone is using, which is the internet at the moment. And yes, and the reason why I'm not going to talk about what we are talking or why we are in stealth and is because you need a business justification to go out of stealth, or at least to explain why we are, and we are just holding this car to serve more customers. I mean, that's the main reason. And for now, as a small company, as a small startup, we can't serve everyone. So we are, cherry picking our customers. So yes, this is not what I'm going to talk today. Today, I'm going to talk about how to innovate in data center. I'm going to be loyal to the request about data center. And yes, and Ruti is going to cut me kind of short. So that's my point. Yeah. Next generation compute, this is what we do. This is NextSilicon. And there is all the other company that innovate in next generation in doing things in hardware. I think that we are the only company, at least, I don't know, every startup in the world, that innovate around the software. And my point is that in order to be dominated the next generation computation, you need to be, you need to understand the software. So that's my talk, and everyone wants to watch the game. Can still make it. So that's a cue. And Ruti, feel free to cut me anytime. And that's the t-shirt that I have. Software, hardware, Pong, all computer. This is the point of it. So this is us. And startup is very hard. Doing a every startup is hard. You need to get the funding, make sure you don't run out of money, and you need to get to your KPI, and get talent, and get more money, and get market, and then have fixed bugs.
Wasting the money is easy.
Yeah. But you need to be focused. Doing a semiconductor means that you have two startups in one place, both the software and the hardware, which is insane. So you need to focus. So in this talk, I'm not going to talk just about innovating, but how to be laser focused about what you're doing. Make sure to reduce the risk, because that's the #1 key of success. And it's not that we are doing the best job at it, okay? The 20%, 80% gain rule that everyone knows makes sense, but it's very hard to follow. And I think that in NextSilicon, we incubate maybe 6 or 7 type of different projects. And I want to thank Eyal, my partner, who is sitting here. Yeah, so Eyal is leading the engineering, which means that he gets all the blame. Well, so data center is hard, and Ruti, I'm going to use some of your ideas inside my presentation. And data center is like extremely hard. And in order to be installed or become one of the hyperscaler customer, you need to do a lot of work. And and I don't believe in 0 to 1 approach. I mean, working 10 years and waste $1 billion, and then here's the best product out there. Everything is in steps, so you need to grow your business, where you're going, where you're heading. This is a must, and Ruti asked me to be very technical, so I am going to be very technical until he will tell me, come on, time is moving. But I also want to talk about the market because it's not less important than just the technical solution. And what I wanted to show in this picture is that deployment at scale, when you have thousands of nodes, is very different than a product that works. I mean, you can have a product that works, but when you go to economy of scale, lots of things happen. And so yeah, okay. So let's go to a slide that Ruti mentioned about the general purpose CPU and going up to a performance one. So back in the days, 1972, Intel came out with the 4004, which is the first commercial microprocessor, which was very successful. And the nice thing about CPU is that they are general purpose. Maybe they are not outperformant out there, but you can just take code, run it, compile it, and it will work. And not getting into the trap about Moore's law, but it was easier to double the transistor and the performance until it converged. And you can keep with a single core, and it was fine. And it served the economy. You can just take your design and change the transistor and no technology in Intel and just move forward. But then it's become harder. So we invented many core. It was first it was multi-thread, and then it was many core, which get to the limit of the CPUs, and then GPU came into the place. And the downside of GPUs, not just they are more expensive, but they introduced a domain-specific language, which means that now every accelerator say, hey, dear customer, just rewrite your code and get more performance, and it has its downside. And I'm going to talk about mostly around the GPU portion. And we talk about FPGA, and there is the ASIC kind of concept. Well, let's build a chip per innovation, and for the guys who are not developing chip. So ASIC means I have a problem, I know what the algorithm is, let's take the best hardware engineer out there, let them sit on the design, write a very dense this is a portion of our chip, I don't know exactly where, maybe I can read the signal, but and have a dense floating point or integer and memory operation and put the SRAM locally inside the core, and you are going to get the best performance out there, period. Example for that is Bitcoin miners that are custom chip that companies are doing. There is one algorithm, Markle root, double SHA-256, and no one can outperform them, not CPU, not GPU, not FPGA, period. So now, why not every application is an ASIC? And I mean, there used to be, back in the days, there used to be a specific chip, like the Anton machine, which did fluid dynamic or molecular dynamic, I can't remember. And the answer, and I'm going to let Grace Hopper introduce, is that amount, $120 million, which is a lot of money. And Grace Hopper developed the compilers and the linker, and yeah, that's a lot of money. And this figure didn't come out of nowhere, because if you know what you're doing and you get the best talent, and let's say the cost of 100 employees is $36 million a year, rough numbers with today inflation for 3 years, because you need to do 2 years design, half year until you get the chip back from Samsung Foundry or TSMC, and then another half year of production. And you need to pay $30 million for vendors. We have here ARM and Poteantec, and you need to pay various for their solution. I mean, it's a lot of money, just the cost of the tape out itself. So just take it into account. No one is going to give you this check unless you reduce the risk. There isn't any seed company that raises so much money. So again, and I think that I want to circle back to Ben that says about the Israeli mind that incubate a lot of ideas, but I think it's related to the Israeli chutzpah that we don't know where we are going and how much money we need, and we're just crazy. And yeah, here we are with a lot of semi companies. All right, so with that in mind, why there is a lot of semi-innovation, especially in the data centers. And if you look at, I mean, that's the investment in semi-startup, and you probably don't see the screen, but just up to this point, $6 million were invested in semi-company. Last year it was around $8 billion. And lots of money is being poured into a semiconductor companies. I mean, what's the point of it if you need to spend so much money and the risks are so high? And the answer is just one. That's the grand price. In order to be the next generation compute, you can be a $100 billion company. And there is NVIDIA and AMD and Intel. And now it's almost end of 2022. Recession is like really bad. Sales are going down. But if you read the report, you see that the element that is going down is mostly the consumer, but data center and HPC and high performance computing, the supercomputer, is keep getting up because of the demand.
There's also Google, Microsoft, and Meta.
So I stay about the next generation compute because yes, we can take other type of company that are doing a lot of other things, but they're doing it to themselves rather than to be a vendor for other leader of compute. And another idea I'm going to steal from Ruti, and this is where I'm going to spend my time on, is like the 6 aspects that you need to dominate in order to win next generation compute. So we used to have the CPU, just the CPU. Single thread performance, let's just write one code that works perfectly. And I'm going to talk a little bit about that. The acceleration aspect, and I put the GPU as the category of accelerator because there are many accelerators out there. And my claim that in order to be dominant in the compute world, you need to win the accelerator market first and then move to the rest. Network storage, that probably you know more than me, memory and AI and machine learning. I was debating whether I want to put AI and machine learning as its own category or under accelerator, but for the purpose of this talk, I put it separately because I want to claim that everything is marching towards commodity. This is Professor Thorsten from ETH Zurich, and in the last supercomputing, he gave a point that if you look at the history, it used to be a custom CPU. It used to be a Cray one, and now you don't see a custom CPU. You are seeing a commodity hardware that is in place. With GPU, it's really a commodity. I mean, each one of you can buy the GPU that has in Azure. There is no a custom fit. Moving to storage, and that's a commodity. Yeah, you can do it better, but you can still buy it. There is no hard-coded customization. The only aspect that differentiates high-performance computing or supercomputing from data center at the moment is around the networking. When you have InfiniBand, OmniPath, other type of interconnect and fabric, and Thorsten foresee, and I tend to agree with him, that in the future, whether it's going to be 5, 10, or 20 years, it's going to be converged and be as well, whether it's going to be Ethernet or some other kind of transportation. History tell Ethernet, but we'll see. So I'm going to touch base on that, and I think that it's around the accelerator. That's a hint. This is why I put it in the center and bold. But before going into the technical details about why I'm saying that, let's talk about the go-to-market. And whatever you are innovating in, whether it's the memory aspect or the CPU, you need to think about your customers. And I put here like 3 kind of sector because you can go to all computation or enterprise computation. You can go to just a hyperscaler to become dominate or high performance computing. So each one has its own price reward. And the numbers here are a bit wrong. But HPC supercomputers is a $50 billion market. Why? Because NVIDIA market cap at yesterday is $400 billion. 12% of NVIDIA revenues is HPC. And they are selling $2.5 billion. And you just do the multiply. That's roughly a $50 billion kind of company. And then you can move on to go to the hyperscaler, which is $150 billion market cap, and then go to all computation. And that's the leading compute. That's why I put $400 billion. And everyone say, well, hyperscaler buys $1 billion every year. Just go to the hyperscaler. And I claim that this is wrong because when you deploy at scale, your product needs to be extremely mature. And if you look at NVIDIA, for example, they started at consumer. In 2009, they moved with the Fermi and Silicon graphics, SGI, to the HPC. This allowed them to get a footprint, and that's the point of my talk, mostly around the software, to be dominant and understand how you connect everything, and then they can go up to other vertical. So it's important to know what is your go-to-market strategy when you innovate around compute or whatever markets that you have. Just give it a thought. Now, circling back to the technical details. So I innovated in storage. I don't know nothing about. There is other companies. We are working with Weka and VAST and DDN, and the challenge there is how to feed the compute system. The reason why I say storage is so much important is because if you build a compute but you can't feed it with data, it doesn't matter if you are running in 1 million cores, but you can't feed them. So that's a key aspect. It's mostly dominated by software, and Moshe talked about how you index the keys and the data structure around the NVMe disk or the HDD disk. Again, I don't know your product right. So it's a different kind of challenge. Memory, it's a cyclic market, yes, up and down. It's dominated by Samsung and other names. Can I say? Micron and SK Hynix, their margin are low when there is oversupply. When there is high demand, margin is going up. It's very hard to innovate there. So there is the HBM, and there is DDR. And I think that essentially what I learned over time is all the semi company essentially is a sell channel to Samsung to sell their memories and their HBM, and we are a good example of that.
And the CXL memory.
And the CXL is the interconnect itself, and that's the next slide around the networking, because whether you want to communicate within the node itself or outside the node, that's the interconnect and the network. And yes, there are going to be protocols that will be dominated. And I think that one of the reasons why NVIDIA acquired Mellanox is because they say, well, we have a GPU, we wanted to acquire ARM to be dominated in the CPU, and we want the networking. And at the moment, there isn't any networking company that don't have a compute solution of its own. You have Slingshot, which is HPE. You have Mellanox, which is NVIDIA and NVLink, and that's InfiniBand. Hopefully, it will stay open because it's an Israeli company that gave a lot of pride, and their products are really, really good. But you need the networking to move the data. InfiniBand, by the way, InfiniBand design was to be within the node as the CXL is. Just saying. All right. Do I have another 5 minutes?
5 minutes.
All right. 10 minutes. All right. So CPU, okay? And Moore's law, we used to have 2,000 transistors back in the 404. This is, by the way, the 8086, which has 26,000 transistors, and now the AMD APIC has 90 billion transistors. So it's keep going, and no one can predict the future, and transistor can go up, and Samsung has gate-all-around. I mean, we still have a path forward for the next 10 years. Maybe there will be more materials. I don't know. Developing a CPU is hard. I mean, we started with a three-stage CPU, right? That three-stage pipeline to do things, and now we have a complicated reorder buffer with 400 instruction and 3 level of branch prediction and more units, and the design of a core become very complicated. So this is our floor plan, and I abstracted it because there is a lot of nuance there. And then we say, okay, who developed a CPU? It used to be Intel and other x86 licenses. The leading edge is now Intel and AMD, and then you have ARM developing a very good cores that sells to Graviton in AWS, and Microsoft has them, and AWS developed their own core based on ARM instruction set license. And Google, they're doing their own core, and Fujitsu is doing the A64FX, which used to lead the most powerful supercomputer up to last November or June. And Qualcomm, they're doing their own cores. So what's going on? And this is my point. Most of the IPs and patents around how to design a CPU, the know-how is out there. If a company wants to build a CPU, they can say, well, we get the best talent out there, we'll pay them $1 million a year salary, we'll get 100 of them, and with a 3 years or 6 years, with a few generations, we can get to a CPU, and then it's just a matter of total cost of ownership. If I'm building 1 million server every year, instead of paying a premium, I can license ARM core, I can develop my own cores, there is RISC-V cores, and it's going to be a commodity. It's going to be a commodity, it is a commodity, and you will see more and more companies develop their own single-thread performance, and there is a lot of embedded vendors, but we will see in the next few years a lot of change around the high-end kind of core, and it just makes sense. And with the accelerator, the situation is different. There are many companies doing, specifically AI and machine learning, and I don't want to talk about it, but there are 2 companies that dominate it. I changed the color from the website, so no one knows who is who, but obviously it's AMD and NVIDIA, and they look the same, because the difference between GPU and a CPU is a many-core architecture with a non-standard, non-coherent memory subsystem, period. And you see a lot of companies saying, hey, that's the best processor out there. And I was able to squeeze with hardware design and photonic and analog design, how much? Teraflops or hundreds of teraflops or a petaflop, I don't know, I'm hearing in 1 bit. But it gives challenges to the users because, yes, you might develop the best hardware out there, but unless you have the software stack, no one can use it. And, and there is a different level kind of support. Hey, look, I developed my own kind of chip, but just use my framework. You can use my BLAS subroutine included, and it will be fine. Or it can go deeper, change it to language directive, or write in your own, on my domain-specific language, and you need to learn my architecture and my microarchitecture. You need to know where the memory is located, and you need to have a background thread that moves the memory around, and there is a lot of reduction unit that you can put. I mean, that's simply hard. And moreover, it might not pan out. And the cost of not paying out, and I took the picture of John Bacchus, who is the founder and wrote the Fortran code. And I don't know who knows what Fortran is, Fortran language, but yeah, the old guys. Surprise, surprise, most of the scientists that are doing science using Fortran for a production supercomputing application It's got huge support, and it's still out there. And taking that piece of crap, porting it, it's just hard. It can take a few years. And if it takes a few years, you run it, and then nothing happens. You get, let's say, 20% speed up, but the cost of the hardware is 2x. So I'm net negative, not including the salaries I paid, the time I got wasted, not including the fact that suddenly the algorithm have changed. So I need to start everything from scratch. So what did I do? And moreover, once I did the port into the domain-specific language, I'm become a vendor lock. I'm being captive because I'm using the toolchain. I already invested in the software, so I'm there. How I can move out of it? And the reason why, this is an article that you can all read by NVIDIA CEO saying I'm spending $1 billion a year on software and library and framework that it will be easier for users to port to my NVIDIA and my CUDA. Means that no other semi company can compete. Because guess what? Even $100 million is very hard to fundraise. How can I support this software? Doing whatever I can to focus on these few hardware blocks. I don't have time to port every framework to use my hardware. And then, yeah, so it's all about the software. And we are NextSilicon. We are doing things in a very different way. And last point is the name NextSilicon and the logo, what NextSilicon means. So you have the HTML logo, you have a silicon which is a chip. You combine them, and you get our logo. And yeah, and that's the end of my talk. So 30 minutes, and I said nothing.
So, Elad, thank you so much.